Okay. Welcome everyone to what I think is our second last LEAP lecture of the semester. And we're very honored to have Veronica Eyring join us. Veronica Eyring is the head of the Earth System Model Evaluation and Analysis Department at the German Aerospace Center. It has a German name, DLR, which you're free to translate. Institute of Atmospheric Physics. And she's also the professor of climate modeling at the University of Bremen. Her research focuses on improving climate models and projections with machine learning and spaceborne Earth observations for actionable climate science and technology assessments in aeronautics, space, transport, and energy research. So we can see that there's a lot of synergy with her research and LEAP. And she's a very accomplished scientist, and I won't go through all her accomplishments, but two stand out, to me at least. Veronica was the head of CMIP from 2014 to 2020. And second, she's affiliated with NCAR and also a co-PI on the European Research Commission grant, Synergy grant, along with Pierre and two other colleagues at Jena and Valencia. And the grant is called Understanding and Modeling the Earth System with Machine Learning, USMILE. And so that's how I know most of Veronica's work. And the grant has funded some members of LEAP and Pierre's group. And so today, okay, everything good? So today, Veronica is going to tell us about improving Earth system models with machine learning, a next generation Earth system modeling approach. Thank you, Veronica. The floor is yours.
Thanks so much, and great to be here. I had to cancel my talk in summer. I couldn't visit, and I'm very happy that I can join you today, and it's very exciting to talk to all of you. As we've already heard, I'm working quite closely with Pierre Chantin, that maybe not every one of you knows. So the work I'm going to present today is part of the ERC Synergy Grant USMILE, Understanding and Modeling the Earth System with Machine Learning. And I'm a PI together with Pierre Chantin, Gustavo Kamsweiss, and Markus Reichstein. So Pierre is not only a great LEAP director, he's also a great co-PI on USMILE, and I so much enjoy collaborating, and we will continue this collaboration as we move forward with hopefully joint visions to reach ambitious goals. So today I will present work from my own group, and we are focusing on machine learning atmosphere, and I would like to acknowledge my group members and also our collaborators. So some of my group members are going to be online, I hope at least. I haven't seen them, but they might join the discussion depending on how it goes. And we have Katharina in the room. Katharina is also a PhD in USMILE and is actually our closest LEAP USMILE collaboration, as she has worked here through an internship last year and is also going to stay here until early February again. So she's also happy to present her work. Okay, so USMILE. USMILE, we are doing 4 different topics. We are working on machine learning-based observational products. We are working on hybrid models, focusing on the atmosphere and land, knowing well that there are different components in the Earth, but this is what we focus on. And we also develop machine learning algorithms to better understand and detect patterns of climate variability and extremes. And we are constraining feedbacks and projections in climate model projections. With machine learning, in particular causal discovery. So today, due to kind of the time, I'm focusing on the hybrid modeling. And in particular, I will focus on the atmosphere. And just so that you know, you are working here mainly, I think, with CSM, maybe also SBCAM and other models. And our model is the ICON model, which is the German climate and Earth system model. We are working so far with ICON-A, which is the ICON atmosphere model, meaning we're not yet, everything I'm showing you is not going to be coupled with the ocean, but we are moving ahead now with full speed towards CMIP 7. and we are going to transfer to ICON-XPP, which is going to be the CMIP 7 version from Germany that we will contribute to CMIP 7. And we have managed to convince people that it's good to additionally have a machine learning based version. So our target is ICON-XPP ML, at least in AMIP simulation. I'll come back to this later. So in terms of the talk, I have heard from Pierre that you are quite familiar with climate modeling. I will still briefly state again the motivation. So why we are doing this research, and then I will guide you through our work, mainly through a variety of PhD theses we have done throughout the last years since the start of USMILE. And we are actually the first USMILE PhDs are finishing now, and we are going to hire the next round with new goals. So I will start with a feed-forward neural net on cloud cover, and then we worked a lot on improving trust, reducing biases, and on generalization. I will show you 4 examples from our group, starting with equation discovery and the issues we have with the traditional feed-forward neural nets. And then I will also present very briefly that we are also working on acceleration of ESMs, in particular radiation works done by Katharina. And I will close with machine learning challenges, briefly also have slides on, well, we are developing a climate model, so we need to retune. We had to go into this as well. When we take out a parameterization, we are losing parameters. There we are, we have to start again. And also I would like to introduce you to the system model evaluation tool that my group develops as a co-PI with 60 institutions or more. And this is traditionally now has grown over the years, and we have used it in IPCC as well. And you can utilize this tool also for evaluating your simulations. And I will introduce you to how you can get in contact should you wish to do so. Okay, and I close with a summary and vision. So let's motivate briefly our research. You probably all know the coupled model intercomparison project by the World Climate Research Program. I chaired the 6th phase from 2014 to 2016. And CMIP 6 is really a huge, a fundamental source for scientific understanding and also for IPCC AR6. So you see here 2 examples. The upper one on the upper right is attribution. So by doing simulations with all forcings and then taking out the anthropogenic forcings, we could clearly conclude that it is unequivocal that human influence has warmed the atmosphere, ocean, and land. So that's one of the main tasks of a climate model. You can take out forcings, you can do sensitivity studies, and so on. So it's extremely valuable. And also in the lower panel, you see the climate projections from CMIP 6 for the 5 scenarios that were chosen. And you can see that only in the upper left, global warming remains below 1.5 degrees with a small overshoot, whereas in all other scenarios, warming is much higher. And this scenario is the one, the low scenario is the one where CO2 emissions immediately decline. They get net zero towards 2050 and then negative. So this is really important information and also very robust information we have derived from the CMIP 6 models. We could also show, and this is work has also been done as part of IPCC. This was chapter 3 that I was coordinating lead author together with Nathan Gillett from Canada. And we could show that the models are improving. In particular, you see that CMIP 3 is the previous phase, and 5, and then 6 in purple. And you can see that for the key indicators of climate change, here just as an example, near surface air temperature, precipitation, and sea level pressure, we get an increase in correlation with observations. So that's good news. We did this for quite a large variety of different key indicators of climate change, and it was throughout that the models are improving. However, And that's really the motivation why I already in 2000, when we saw it, that I mean, there was no improvement basically in some of the systematic errors. And that's really quite an issue, in particular because the questions we have asked before, like, is it human-induced climate change? Yes, that's not the question, to my mind at least, that we have to answer now. We have to go more regional, and we have to be much more accurate. And you see these biases here in precipitation, and they are quite big. So this is the double ITCZ, and I really would wish and dream from a climate model that doesn't have this bias. And that's motivating our work. In addition, this uncertainty propagates into projections like the climate sensitivity, but also the even for global mean temperature, uncertainties are large. So can we do this better? That's the question. But let's first ask why. So why is this? This is because our climate models have a specific horizontal resolution. They were like, let's say, between 50 and 160 kilometers in CMIP6. And they are going to be maybe a bit higher resolution, but not super high in CMIP7 either. So what we have here is that we have a lot of subgrid-scale processes that we can't resolve, and there are different ways of representing them in the models. And this is actually causing these uncertainties. So our approach in USMILE is that we take the revolution in machine learning, and we started writing this proposal already in 2018. So it's quite a while ago. We utilize high-resolution cloud-resolving models. They can be run for shorter times. So we take them as training data to learn fast subgrid-scale processes. And we utilize Earth observation. And our goal is to develop a hybrid climate model, as I said, focusing on land and atmosphere. One moment. So, to reach improved projections, that wasn't me, was it? Improved climate projections and understanding. Okay, so that's our vision. That's our vision that we had when we wrote this proposal quite a while ago by now. Hilfe. Das bin ich. But I haven't changed anything. Moment. I'm fully muted here. Is it better?
You ask them to mute.
Is someone unmuted? Not muted? Oh, now it's better. Okay, thank you. Okay, so here's our approach. So you see here that we are, this is a short kilometer scale high resolution model simulation. We coarse grain it to the resolution of the Earth system model, say 80 kilometers. We coarse grain the state variables, and we coarse grain the tendencies that we want to learn. And in this case, we want to learn cloud cover, and then we train a neural net with the output being the cloud cover in each of these grid cells, and the input values the potential features that could possibly determine cloud cover. So that's basically our fundamental approach that we do. And why do we do this? So the cloud cover parameterization in ICON is based on the Sundquist scheme. It's very kind of nearly entirely dependent on relative humidity, and it has, compared to observations that you see here, it shows that, for example, cloud cover is overestimated higher up and is underestimated over Barbados. So this is only one example. So there are quite a few biases in this parameterization. For this particular study that we started with, we used training data from Narwal, which is the region you see here, 2 months at 2 to 5 kilometers. And we also used cubic and diamond data. These were global data. So we learn from these simulations, and then this is work that has been done by my PhD student, actually jointly supervised by Pierre, on Arthur Grundner. And you see that we could, by using the approach I just showed, we could reproduce the high resolution simulation quite well. So Arthur here trained 3 different neural nets, type of neural nets, but I'm not going to go into detail here. The neighborhood-based neural net that included the cell of interest plus the vertical levels around it and the lower level. That one was the one that performed best. And it actually showed an R-square value generally well above 0.8, and it clearly outperforms the physical scheme. So that's good news. But however, with this first approach, we saw that we had issues with generalization. In particular, globally trained neural nets can reproduce subgrid-scale cloud cover of the regional storm resolving model simulation. However, neural nets trained only on the region of the Narwhal region didn't generalize to the globe. That might be okay. So I think that's also still a kind of a question, is the training data, and we might want to go much better in this regard in the future by joining forces, for example. Okay, so we had problems and we wanted, so this was one of our first study with this approach. And so we wanted to now work further towards improving trust, interpretability, generalization, and also acceleration. On this slide here, you see a variety of different studies that we did. I will focus and show you in this talk equation discovery, which I feel is very promising, and also a study by interpretable multiscale machine learning-based convection from Helge. And we have also worked quite a bit on causal deep learning. I can talk to that afterwards if you want, and on stochastic neural nets. And Katharina recently submitted a paper on machine learning-based radiation. This is emulation. This is to make the models faster in order to allow higher resolution. So I will start with equation discovery. This is an alternate approach compared to the neural network approach I just showed you, again, done by Arthur Grundner. And the idea is that we want to find an interpretable, flexible, simple, and accurate equation from data. So it's learning an equation from data. And the motivation is that we want to increase trust and also increase generalization. So how do we do this? When you want to compare the different cloud cover schemes, we did this on this plane where we plot on the x-axis, we plot the performance, and on the y-axis, we plot the number of parameters. So you can probably imagine that we ideally want to have an interpretable equation that is not too complex, but still has a very good performance. So it's something we want to see is here with an R-square and above 0.9, but maybe not as complex as our neural nets. Because remember, we want to put this all into the ICON model later on, and it will just increase our computational time. And if we are too high in terms of computational time, we haven't won very much. So that's really our concern. And here we start, so in the blue boxes, blue dots here, you see the neural nets from Arthur's first study, very complex, very good performance. And what he has done then is that he used sequential feature selection neural nets. So he selects, here we select the most important input features one by one. And at each step, the feature is chosen that maximizes the performance of the neural net. And then we can go through that one by one. So let's do that. So here are the neural nets from the first study, very high complexity, but very good in terms of performance. Here are the traditional cloud cover parameterizations. So you see they are really not performing very well with a mean squared error of around 800 in the current Sundquist parameterization. in this particular case. And then Arthur has added SFS, has added polynomials and linear fits. So they are still better performing. We are doing this feature selection to show one by one what features are important. And then we plot the Pareto frontier. And what we ideally want is, because the sequential feature selection doesn't give us an interpretable equation still, ideally we want to have an equation that is somewhere down here. And for this, I guide you through that. Arthur has used a routine that's called PySAR. And this is a symbolic regression. I'm not sure anyone of you here has already used it, but it's quite powerful. So when you we run PySAR and select the equations that satisfy all physical constraints. So for this particular example, we had 7 different physical constraints. And then you can start choosing the different parameters and operators in the equation. And then you start with a random population of equations. You keep a specific fraction of the best equation, and then you mutate and go back to step 1 until you have found an equation that fulfills your physical constraints. And the one he found is this down here. F of x is c plus b minus 1 over a. And this particular equation has a root mean squared error on the entire validation set of 83. So it is definitely a lot better than the Sundquist. And one very important part, and that's why I wanted to show you this, because I think we can apply it also to other physical processes like gravity waves, is that he has found a new term that really enhanced the marine straticumulus and could therefore reduce this bias. So overall, this equation sits here. It has a very good performance and low complexity. And here is what this equation does in terms of the second term. And this second term clearly enhances marine stratocumulus clouds. And that's something that really goes into the right direction in terms of reducing systematic errors. So we believe here we have a novel, highly accurate, physically consistent, interpretable, data-driven equation for cloud cover. And Arthur is currently on this was all offline, what I showed you. And he's currently doing an online simulation here. And he could show that we have significantly reduced biases compared to observations in a 20-year ICON-ML AMIP simulation. So here in the regions which I just pointed you, you see here down here the original ICON-A model with the Sundquist data, and here the data-driven equations cloud cover, and you see that the biases are removed. Not removed, reduced. We can't expect that they are totally gone, in particular because cloud cover isn't the only parameterizations we have in the model. So we are working on others. I will show you some more examples. And overall, this is working at the moment and also having improvements in radiation. Overall, this is quite promising work. There's a lot to be done also on the mathematical side when it comes to applying it to more complex problems. The current problems with the methods we have used is that it can't take too many input features, and cloud cover is, so to say, an easy problem when you only want to predict one value in one grid box compared to convection. But still, I think that's a topic we could further explore. It's also very physically based. Okay, so let's move to the second example. This is biases due to convection. So this is another kind of major bias, and you know probably that conventional parameterization have biases which are reduced in storm resolving models. So these are the precipitation. Also in several of the high resolution models, the WITCZ bias that I showed you earlier is removed or reduced, and so on. So there's really hope that with increased kilometer scale, these biases reduce. And the question we asked was which machine learning models are particularly suited for the parameterization of convection for learning this process from the high resolution short simulations? Can we connect learned relations to physical process understanding? And can we achieve stable runs with a machine learning based parameterization? Okay, so this is work by Helge Heuer. I think he's online for discussions, and he has tried a variety of different neural nets, and the one he found that worked actually best in the case for convection was a UNet. And one thing we wanted to point out here with this slide was that indeed we need to check for spurious correlations in our neural nets. What he found with this UNet here is that the full UNet he first applied learns actually a reversal of causality. So when the machine learning model sees precipitation, it guesses that convection is responsible for rain and snow. And while this is maybe okay or makes sense, it doesn't really, it's not the right process when you put it in the ICON online model. So it should be kind of reversed. So that's why these sub values really highlighted this, and he moved to an ablated UNet. And I will just go very briefly now over the results of the following studies. And here you see that, there were a few pre-processing steps required by filtering and calculating subgrid fluxes. He developed machine learning schemes that were conserving energy and showing good performance offline. That is already published, this paper. And we benchmarked the derived UNet to a variety of different machine learning models. And this ablated one really performed best. And what is extremely promising, I told you in the beginning that really we want to improve upon the long-standing systematic errors. And here you see the precipitation extremes. And in blue, you see the high-res simulation. In green, the conventional simulation, and in orange, the ablated UNet that he developed. And you see it's a lot better compared to the conventional scheme. So not saying this is a proof, these are at this stage, to my mind, just indications that we can do better in these systematic errors. We all still have to develop the full hybrid ESMs that run AMIP and CMIP simulations. But this is great news. However, he also found, and please now watch, this is not, one moment, it's not running. Okay, one moment, I'll try again. Yeah, now it runs. So you see this is vertically integrated water vapor, and you see the issue here that initially it looks fine, but then as the simulation continues, it's actually too blurry, and this is too smoothed. And I think this is something we also need to watch. It's a typical machine learning feature that we need to be very careful about. So with this, we concluded that we have to further improve, and I just show you how we did that. Some of you might know the ClimSim data set. Actually, I've learned some of you were even involved in the competition, the Kaggle competition on the ClimSim data set. So Helge has now also switched to this data set to further improve the approach. He actually used the Kaggle competition winners and tried them out for convection first in ClimSim, and has then ported this to ICANN, and in particular with the goal to improve the approach towards being not so smoothed out. And indeed, when you look now at this simulation, it is a lot better. In this particular study, he has removed the radiation and the tendencies part in the part in the tendencies that comes from the radiation routine. That is required because he focuses on convection only. So there are still a few things to further work on, but this is kind of where he stands. And we are hopeful that with this approach, we are getting a machine learning based convection parameterization into ICANN that runs stable and outperforms the traditional parametrizations in ICON. Okay, I'll show you two more examples from this side. So the next one is a study by Yannis Klamt, another PhD student from USMILE, and he has worked on improving the planetary boundary layer height in ICON with deep learning. And here we are not learning from horizontally higher resolution, but from vertically higher resolution. And the motivation is similar because, again, there are quite a few biases in the traditional model. The planetary boundary layer height is a key input to turbulence, as you know, and the classical boundary layer height scheme has actually quite some biases, and I show you just two here. There is compared to the high resolution simulation, which is in orange, and the blue is, the orange is the low resolution and the blue is the high resolution. You see that the low resolution has a bias towards a smaller boundary layer height, and also that there are numerical artifacts in the relative frequency. So this was his target. He wanted to improve upon that. And the strategy was that he performed vertically highly resolved global simulations with 250 levels. And then he vertically coarse-grained to the target resolution in ICON, which was 47 levels, which is a version that has exactly the artifacts that are shown here. And then he developed a deep neural network that predicts the boundary layer height. And with this approach, he could show that indeed in the offline performance, in the training, and in the validation, he had great correlation with an R-square of 0.992. And also he could remove some of these, he could remove these artifacts, and also the relative frequency looked a lot better. You can also see this in this movie here. So in the upper part is the high resolution, in the middle is the low resolution, and in the bottom is the deep neural net. And oops. Yeah, and you can see that the bias in the middle is a lot higher, and also that the deep neural net is improving upon the low resolution version substantially, with an average boundary layer height that is higher than in the low resolution. And on the left-hand side, you can see that also the diurnal cycle improved. So when he put this online, that does have an impact also in the online simulation. That's again an AMIP simulation with ICON 35 years long. So it's running stable, which is fantastic. And we see here that, as I just mentioned, the boundary layer height is compared to the classical scheme is higher on average in both seasons that he showed here, June, July, August, and winter DJF, and also has an impact on surface temperature. And it also has an impact on cloud cover. On the left-hand side, you see the bias compared to observations for cloud cover in the traditional ICON model. It is quite high. And with the boundary layer height, we are moving in the right direction, although it's only a tiny contribution when you look at the percentage. However, we are hopeful that now the next challenge we want to add, we want to take is that I've shown you now cloud cover, I've shown you convection and boundary layer height, and we want to implement these three all together in the ICON XPP model. And then we want to run an AMIP simulation and want to hopefully, with a goal to hopefully reduce the systematic errors in this simulation. So the studies I've shown you so far, and that's in fact where we stand at the moment, is that different PhDs and postdocs have worked hard on their machine learning-based parametrizations. And now it's really a group effort to get this together to build the climate model, because that's not something that can be done by a single PhD. We have to retune, we have to run the simulation and so on. So it's a huge effort. Last study from the individual studies I show you is the study by Katharina. So Katharina has developed an interpretable machine learning-based radiation emulation for ICON, and radiation is a very expensive routine. So here the goal is really this acceleration in order to have a faster Earth system model in order to move towards higher resolution. And the emulator consists of these 4 different neural nets, and they can efficiently and accurately emulate ICON's radiation scheme, which is the one developed by Robert Pincus. And the neural networks are statistically energy consistent without explicitly enforcing them. And the bi-LSTM learn physically meaningful relationships related to the locality of the problem. So temperature, when you look at the sharp values, here is temperature, and here is the tendency, and you see that this is more local process, whereas when you look at the cloud fraction and the tendencies in shortwave in temperature change due to shortwave radiation, you see that this is much more a non-local problem. And that is really a quite nice study. Katharina has submitted now, and she's now working on a second paper where she's using FTorch and couples this to ICON, and the radiation routine is twice as fast as the traditional schemes and works in overall stable. So that is work Katharina is doing now, and she's going to stay here. You know that she was here last year with a DRD internship, and she's staying again now, mainly with Sarah, but she said she's coming every Thursday. So we welcome your collaboration on this study, and maybe if you want to know more about this, Katharina can also speak in a seminar. Okay, so I close this part by telling you that I feel that we made great progress, but we are long not there. We still have a lot of work in front of us. And here I showed you some examples why this is really promising, and I add 2 more. So I've shown you in the study by Helge that we can, we have a good indication that precipitation extremes improve with our machine learning-based convection. We can have a better cloud cover, hopefully, with equation discovery and also with a boundary layer height. We have additional studies on machine learning-based stochastic parametrizations, where we could show that we could improve the diurnal cycle of precipitation, another major systematic errors in the climate models. And we also had a study with SBCOM. And here in red is what we called a causally informed neural net. And here you see that with this causally informed neural net, we could really reproduce the SBCOM simulation. And if we did that, then we would have a reduced double ITZ bias, which would be just wonderful. So these are indications of, yes, we are on the right path, and now we have to bring together the puzzle. What I think we should further work on for sure is machine learning challenges that come along the way. And we have had an HGCI workshop where we discussed this with a large community, with a community, with representatives of the community. And in particular, machine learning challenges, as we concluded at this workshop, lie in the physical consistency, stability, and generalization. So we want to work further towards including physical constraints or other approaches for stable simulation and generalization. I think we have made great progress actually overall on this topic, but certainly in terms of generalization and stable simulations, we can further advance. Uncertainty quantification remains, and including ensemble generation for we just heard from Tim, for having being able to quantify rare extremes is going to be very important. Explainable artificial intelligence is something we could also further utilize in order to learn more about physics, because actually what people still sometimes think that machine learning is a black box. I think it's an outdated worry, because we really know we can do feature importance, and it tells us something about the system, which is really cool. And then causal inference, I think there's a lot to gain there. We developed this causal deep learning. It's very tricky, and also it required a single neural nets instead of a full coupled neural net. And we also work a lot on causal discovery, and accordingly on the machine learning side, people work on further improving causal algorithms. Okay, so I want to close with this last topic on how we use observations at the moment. We want to also learn from observations in terms of learning from observations with by improving parametrizations. So far, we use observations for understanding, tuning, and evaluation. We have a variety of studies that use causal model evaluation to understand the system and to evaluate the models, also constraining uncertainty. And we also use tuning. So here is our tuning approach that is following up from previous work on history matching. So one thing that, of course, we need to do when we replace a parameterization in the model, we need to retune the model. And this is a step that really takes time and also costs a lot of computing time. So here we have developed a machine learning-based automatic tuning framework for ICON, or it's not yet automated, but it's working towards it. It's a paper that was just published, and also Max Baumann is working on a similar approach together with Katie Dagan and Linnea Hawkins on the land-atmosphere coupling. So the idea is basically that when you tune, you need to first choose your metrics and identify your parameters to tune. This is a kind of sensitivity analysis you need to do anyway. And then you have an iterative optimization. And the way we do it now is that we calculate a perturbed parameter ensemble, but only with a smaller PPE than in a traditional tuning approach. We fit a machine learning-based model and emulator to the PPE, and then we generate a very large PPE with that emulator, and then we use history matching through a variety of different steps. So it balances between exploration of the parameter space and exploitation of the already explored and potentially promising parameter regions. And this exploitation trade-off is achieved by shrinking the parameter space according to an implausibility criterion. And in this first paper, we demonstrated this, but Lorenzo is now working further on this approach that we hope to utilize to save computing time and also make the approach more objective. And the last topic before I come to the vision that I would like to introduce you is the Earth System Model Evaluation Tool, so that you can utilize it in your work should you wish to do so. So this is a tool we are developing since many years, and it's a community diagnostic and performance metrics tool. It's open source, and we used it in several chapters of the IPCC assessment report. And we develop it with around 60 international institutions and regular releases. So what you can do is you can plot your model compared to CMIP models, for example, so that you see where you stand. Or you can also, this is work done by Manuel Schlund. We have expanded it actually. So when we have a recipe now, and when we run an ICON-ML simulation, we can very quickly evaluate it compared to observation. It's a huge recipe. It's concentrating on several diagnostics, but also has, for example, emergent constraints. And on the right-hand side, you see that you can also benchmark your model within this performance metrics plot that some of you might know. And you can see whether you have improved compared to the rest of the CMIP ensemble, for example. So if you want to use that, you can contact Manuel, or can also go to one of these GitHub repositories or a lot of documentation and tutorials. Okay, so let's close this up. So that's where we stand at the moment. We are developing methods and different approaches, parametrizations for radiation, convection, gravity wave, turbulence, cloud microphysics, and so on. We are developing for icon automatic tuning methods and new methods like causal neural nets and equation discovery. And now we want to bring things together. So our ultimate goal for, like, I would say, not 5 years, that's too late. So we need to be faster. So what we are now doing is, as I mentioned, we bring these things together to a hybrid icon ML. We are going to use XBP, and we will move forward initially with ICON-ML atmosphere, and then hopefully also coupled. Our ultimate goal for CMIP7 is that we at least contribute an AMIP simulation with this model, and hopefully you can do so too with the model you develop. And then maybe a few more could at least demonstrate that we can make progress with machine learning in reducing these systematic errors. And I can't even tell you how important this is, and we can't wait yet another round. So I think we really have to hammer it now. And the reason is that, CMIP is heavily under complaints, and partly this is also correct. I mean, we really need to improve on these models in terms of reducing systematic errors. We do, however, not think that we can do everything with kilometer scale model. While this is a great approach, and this is the perspective I've published with Pierre and Gustavo, Marcus, and Dave Lawrence just now in Nature Geoscience. Our vision is that we really bridge across scales and process complexity. So this approach can be fully integrated within CMIP. It's not an extra initiative. It can also be fully integrated with any digital twin initiative and Eve. So our vision is that we enhance the models with machine learning by learning from higher resolution simulation. This could be even kilometer scale. You have still turbulence and microphysics that are not resolved. But here are the hybrid ESMs that I showed you in this talk that targets maybe resolutions of 40 to 80 to 160 kilometers, which we will continue to require for complex Earth system processes in large ensembles. And these would be improved with machine learning to have really significantly reduced systematic errors. And then we also need to bridge towards more local scales. That's clear. This can be directly done by a kilometer scale, but also by downscaling or regionally refining these coarser Earth system models. And then we are hoping for reduced systematic errors and more accurate climate projections towards more actionable climate science. Okay, so this is what we want to work towards. We are currently here, but in this next round of PhDs, we will much more target this latter chain here, and also creating ensembles, large ensembles with the models to target rare extreme events. Okay, to close, so I have, I hope you know that CMIP is really a fundamental source for scientific understanding and important source also for the IPCC assessment reports. However, correctly criticized for large errors and climate projection uncertainties, and also a kind of a slow pace of updating climate information. And here really machine learning can help, because there are various other ways where machine learning can help the cycle and speed it up in many ways. We develop hybrid Earth system models with a goal to, and we have actually, I think we could say we have demonstrated that machine learning has the potential to reduce systematic errors, but we are not yet at a coupled version. So we still have to show this. So when you do something in the atmosphere, you couple the ocean, you could mess it up completely. So this is something that's still outstanding, at least on our side. We want to further work towards machine learning challenges. And we truly believe that bridging across scales and complexity and communities will be important. In fact, we all need to work together across scales, complexity, and communities, and cannot separate the world into whatever high or low resolution. It's really an urgent problem we have to work on together. And I'm also hoping that I'm really delighted that I get the chance to talk to several of you today so that we can build up more and closer collaborations, not wasting time, not doing things like double, that we might do better jointly. And then we should do it, and we should do it in collaboration and really show that we can do this better. So yeah, we want to bridge across scales, and this could form an integral part of CMIP and digital twin initiatives. And we are trustful that over time, we can really increase the accuracy and utility of climate projections also on the regional scale. In CMIP 7, I think our delta will still be very small, but we have to show it. And that's what we are on. So we are busy, and hope you too. Thank you.
Great. Thank you, Veronica. Does anyone in the room have any questions? And if you have any questions on Zoom, feel free to pop a question into the chat or raise your hand online.
David, thank you. You'll have to switch on. Sorry? You'll have to switch the mic. You'll have to switch on the mic. Sorry. Switch on. Right there. Here? Yeah. Oh, there we go. Okay.
Great talk. Thanks so much for coming in and speaking. So my question has to do with causal discovery and that point you had on an earlier slide about dealing with non-stationary processes or otherwise some combination thereof of moving means, heteroscedasticity, other higher moments moving about. I'm wondering how you deal with that vis-a-vis climate modeling, and also what implications that bodes for the generalizability problem.
Okay, so you are referring to causality in terms of deep learning and parameterization, and not causal discovery for model evaluation. Okay, yeah, so for we actually had the hope, so our thinking was that when you have a neural net and your spurious correlation, it wouldn't generalize that well. That was kind of our hypothesis. And we thought, okay, we hammer it with causal deep learning. And we developed a causal deep learning approach. Basically, each output has a different set of input variables, because we were running a causal algorithm before we training the network. And so we removed all spurious correlations and had for each output the set of parents that are actually responsible driving this particular output, so in a column. But that meant that each of these, that you couldn't do a fully connected neural net. We had, instead of having one with 65 layers, we had 65 with one output. Okay, and then we had to run this before. And in fact, we have further worked on this with another study, but again, by using a completely different approach. But again, we couldn't build it into the full neural net with the 65 levels. So it has helped in terms of making it more physical. And it also generalized, okay, but it didn't improve in terms of generalization. It has a lot of other advantages, but it has the huge disadvantage that it's huge. And we haven't really found a way to do this. I personally still believe that we should further work on combining causality and deep learning, because it makes sense to restrict your neural net and the weights to the physically sensitive, the physical processes, rather than including spurious correlation. But I'm a physicist. So a machine learner might say this differently, but I still think that's very valuable. But so far, the two studies really worked hard on this. We couldn't really do a causal deep learning neural net.
Thank you.
Any more questions in the room?
Very nice talk. I'm curious about the part where sort of in the schematic on the previous page, where you're bridging from DNS, LES to kilometer scale models. I I feel like at least from my perspective with microphysics, a big part of the problem is just that, you know, there's no way to resolve the degrees of freedom of the true microphysical system. So essentially, there's going to be an uncertainty there, and that uncertainty isn't something that's necessarily stationary in space and time, or you know, sort of IID in space and time. It's something that might have spatial and temporal covariances that affect things. So when you then put that into a kilometer scale model, the biases that come out of that aren't necessarily straightforward. And so if we're training that on our climate models on that, there's sort of a, how do we do that? How do we sort of bridge that scale? In particular, because the kilometer scale global models are going to be extraordinarily expensive.
I don't know. But we're thinking about it. So, I mean, in particular, I think, so even we are currently trying to develop microphysics parameterization just for the 80-kilometer model. But then you have the problem that I talked to a few of you, you are having different approaches, which are great. And I think for microphysics in particular, we also need to join forces to and also for turbulence, because turbulence is equally really tough. Yannis is working on turbulence now, but we know it's going to be super challenging to develop a global, like a parameterization that you can really put in globally. That's these are the two topics where I think a lot of research is still required. And one problem, as you say, is, for example, for the 80-kilometer approach, we are currently learning from a very high resolution, but then the microphysics is not like the best you could dream of, because it has to be reduced because of computational expenses. So it's something we just need to further exploit. It's not an easy problem, I would totally agree. And so we are currently, as I mentioned, we are currently at this stage here improving the Earth system model and the coarser one, but we are starting in this direction. I think several in LEAP as well. I'm sorry that I couldn't give a better answer, but I just don't have one.
I have a question sort of about the sociology of this at the broader scale. So like we're all in this bubble in USMILE and LEAP where we think machine learning is great and everything. And we know CSM is also going towards a CSM3 with a machine learning version. But how is this perceived by other groups around the world? Like how many of our CMIP 7s will have machine learning in them, or some version with CMIP with machine learning? Like what? And what's sort of what's the word on the street at the larger scale?
I think we just it's increasing. It was like very low 4 years ago, 5 years ago, and I think we have to do what we always best do, is we demonstrate with facts. So we have to bring out these studies that there is a potential. What I see is, I mean, actually this paper came out very timely. It's I think there is a lot more acceptance also from like so people who would from climate modeling groups, traditional climate modeling groups, I think really see the potential of machine learning. So I know there is a hurdle in the beginning because like we think it's physics, but I think by showing that machine learning is not a black box anymore, that we understand it, that it is still physically based what we get and not like just whatever. I think these are the things that are convincing for climate modeling groups, also not emulating the whole thing, but parts that really need to be improved, and they know this has to be improved. I mean, they know it is. They developed this the groups developed this for a very long time. So I personally definitely see a great acceptance, but for CMIP 7, I would say very few models. And that's why I think everyone who is on it should, I think there is going to be, people are forming together at the moment in something that is initially called AI MIP. So let's get forces together at the global scale, and then hopefully we will have some models that initially demonstrate. And then as we move on, I think the acceptance will grow, because this is such an urgent problem and the biases are so high It's just that we really have to still demonstrate the full potential. We are not yet there. That's another worry I have, but that's why I think I'm still hopeful we make it.
Thanks, Veronica. That was a great overview. One thing that I worry a lot about is, when we talk about our, improvement, and if a model is good, in previous, if you query the literature and you look at diagnostics that represent what people call the skill, like this is a good model, and then you plot that against ECS, the correlations may be 0.5, meaning 25% of the variability explained. And so, and I haven't gotten a feeling that we're defining improvement differently. So if we're not defining it differently, it's a bit scary to think that, because we haven't established what metric cleanly ties to projections, ECS or changing extremes, number of droughts, whatever, that seems to be a problem. And I wonder, diurnal cycle, improving that would be one, important thing to tackle. But there are other things like the covariability at time step output of moisture in clouds, or land ocean differences or mixed phase processes, that you can somehow infer from observations. So I do wonder, I do worry a bit that if we still keep judging models by the typical ways like mean state climatologies, we might have one that all the ML1s look really good in mean state climatologies because of that weak correlation between that and projection is going to come out and we'll see no big difference in ECS distribution. So I worry about that a bit. Do you have any thoughts on that?
I mean, that's one of my main research topics since 20 years. So I think this evaluation bit is super essential, and we should not just look at the performance metrics. The performance metrics are a starting point, but we all know of compensating errors, for example. So maybe there is a model that has almost suddenly no double ITZ bias, but it is just totally bad in other things. So the way we approach with this is that we really we have in this recipe that we are looking at, we target the diagnostics first that really target the possible improvement of that particular parameterization we are replacing, like for clouds or convection first. But we are also doing a lot of work on emerging constraints. So we have we look at what are the measures that really determine the spread. And ECS is one of it, but we also looked at carbon feedback related emergent constraints. And this is what we can do. And I totally agree, just looking at means and of these bulk metrics, as we have in principle shown, I mean, the correlations go up, but the errors remain. And so my answer to this is that we just have to be very careful in this aspect and go deeper and deeper into the models to avoid that there are compensating errors, that the processes are still well modeled, and then we have to do correlation analysis and also emergent constraints to find this out.
Thank you. I think that's all the time that we have for Veronica today. Thank you again for joining and for the great talk.